All right, this is the second hour of Physics 1B for November 3rd. The next thing we're going to be talking about is specifically an adiabatic process for an ideal gas. Okay, what was adiabatic again? Let's refresh. What is adiabatic?
I want to say constant pressure.
Yeah, constant pressure. No, that's not right. What is it? Isobaric is constant pressure. Work equal to 0 is constant volume. No heat added is correct. It's Q equal to 0. Yep.
Heat can escape. Right?
Yep. No heat added or removed, exactly. Okay. Okay. So we want to look at an adiabatic process. And this is one in which Q is equal to 0. So we also know that the change in internal energy has to be equal to the negative of the work done by the system on its environment. Okay. So as an example of this type of a process, let's draw a PV diagram. So we plot pressure versus volume on this axis here. And we're going to look at two what are called isotherms. So we're going to have one that's going to go like this. We're going to have one that goes like this. We call these isotherms. And to get an idea of where that comes from, we know from the ideal gas law that the relationship between pressure, temperature, and volume looks something like this. So if you plot pressure versus volume for different temperatures, so this is going to be, we'll call this one T. We'll call this one T plus dt, right here. So two different temperatures. And of course, the way that the graph is going to have to look is like y equal to 1 over x, basically, right? So, you guys know what that looks like, right? It's a curve that looks like this, right? That's y equal to 1 over x. So p equal to 1 over v is going to just kind of look like this in the first quadrant. Okay, so what is this process going to be? So we're going to move from one isotherm at point A to another isotherm here at point B along some path in this phase space. And then if we want to find like the work done, for example, right, we would find the area under the curve here. And we could label this here to be the volume at point B. We could label this to be, no, not volume, sorry, the x-axis is volume. So this would be the pressure at point A. This is going to be the pressure at point B. This will be the volume at point A, and this will be the volume at point B. So there's our process. And we know we can find the area under this curve here to find the work done, which should allow us to find the change in internal energy. Okay? So let's start off with that equation, that the change in internal energy is equal to the negative of the work done. But let's use the differential form. So du is equal to negative dw. But we know that dw is just pdv. Right? Okay. We also know that even if the process is not a constant volume process, we can see the volume is changing, the pressure is changing. Regardless, we know that we can find the total amount of change in internal energy for any ideal gas simply by computing this quantity here, NCVDT. That will always be what the change in internal energy is for an ideal gas, or at least the simplest way that we can write it down. And then for the right-hand side of the equation, we're going to use that equation right there to replace the pressure. So we'll have negative nRT over V dV. Now, after this point, I don't think I'm going to do any other physics stuff. So, does anyone have any questions up to this point? Adiabatic process, which means Q is equal to W. So normally we would have Q minus W, but the Q is 0. So the change in internal energy is just negative W. We talk about, we change that to an infinitesimal change. So it's du equal to negative dW. We replace work with PdV. We replace P with the ideal gas law. And from here on out, it's just going to be math. Okay? So does anyone have any question about the physics? Looks like that's a no. So what I'm going to do is I'm going to get everything onto the same side of the equation. If you do have a question, just feel free to keep typing, and I'll answer it whenever I can. Why didn't we replace PDV with nRT dt like we did before? So let's go back and look at where we did that before. That's a really good question. We kind of did, though, didn't we? Here we replaced PDV. Oh, isn't the pressure constant in this problem? Yeah, that's why. It's because the pressure's constant, Jacob. So the difference is, if the pressure is constant, right, then dV is everything here. But if the pressure changes as the volume changes, then we're going to have to do some integration, basically. That's kind of the main reason. It's because now the pressure is a function of the volume. That's the main reason why. Okay, really good question, though. Okay, so this now is equal to 0. All I've done is add this to the left-hand side. We can see that there's an in every term, so we can actually just go ahead and erase that away. We can get the t with the dt if I multiply the entire equation. I'll do this in one step. Let's multiply the entire equation by t over cv. The first term is going to become... No, that's not what I want. We're going to divide the entire equation by 1 over cv times t. There we go. The first term is then going to become dt over t, and the second term is going to become r over cv dv over v. Now, I don't specifically remember what r over cv was, but maybe some of you are taking notes and you can tell me. Can I replace r over cv with like something like gamma or gamma minus 1 or 1 over gamma minus 1? What's it equal to? I can scroll back on the notes and obviously find it, but I think it helps if you try to. It's gamma minus 1, right? Is that exactly what it was? Those r divided by cv gamma minus 1, or was it 1 over gamma minus 1? I think this is it, right? I think this is right. Okay. So now we can write it as dt over t plus gamma minus 1 dv over v. Okay. Now what we're going to do... Can anyone guess what we do next? Any guesses? Put a squiggle in the front, right? Also known as integration. Exactly. That's correct. Okay, so we're going to integrate, put a squiggle in front. I like that's a good way to, that's a good answer. So we're going to integrate between our two temperatures. I'll just call this TA and TB, okay? And we'll call this volume A and volume B. We could go back to our picture right here and just indicate that this would be TA and this would be TB, okay? Then our equation will now become a couple of logarithms. So we'll get, for the first equation here, we're going to get the natural log of TB minus the natural log of TA, right? Plus gamma minus 1 multiplied by the natural log of VB minus the natural log of VA. Okay, because when you do, if you don't remember, the integral of dx over x is equal to the natural log of x, and maybe there's some absolute sign value signs in here or something like that. We don't worry about that because we're talking about pressure and pressure and temperature are always positive, right? As long as you're talking about absolute temperature, they're always positive, so we don't need to worry about things like absolute value symbols. And of course, this is all equal to 0 as it was before. All right, so that's a lot of stuff to look at, and it's not a particularly useful equation, but if we rearrange it in the following sense, if we group all of the b's on one side of the equation, and we group all the a's on one side of the equation, then we start to notice that similar to the Bernoulli equation, we've just come up with something that's constant. If we take the natural log of the temperature plus gamma minus 1 times the natural log of the volume, we find that this is constant. So in general, we can just say if we pick any temperature for our gas and we add to that the gamma minus 1 times the log of the volume, we get a constant. Now this seems like a kind of, again, a little bit too complicated of an equation because it has these natural logs in there and we'd like to eliminate those. And that's pretty easy to do. All we need to do is to use some of our log rules. So the first log rule we can use is to say that this gamma minus 1 that's in the front right here can be made to be an exponent of the v, right? That's one of the log rules. You'll remember that rule? You can take a coefficient and it can become an exponent. One of the cool things you can do with logs. And the next thing we can do is we can say the sum of the logarithms here make it so that we can say the natural log of t times v to the gamma minus 1 should also be a constant. And then we can say, well, if the log of this thing is a constant, certainly the thing itself is a constant, right? We could raise both sides to the e power if you prefer. So now we know that this is a constant. And that's going to provide us with a pretty useful equation. So saying that temperature times volume to the gamma minus 1 is a constant is equivalent to saying if I know that a system goes from something like T1 to T2 and from V1 up to V2, whoops, so between two states, right? Then I can turn this into a relationship that says T1 V1 to the gamma minus 1 should be equal to T2 V2 to the gamma minus 1 because they're both equal to a constant. So that's a pretty nice equation there. All right. Next, we can eliminate the temperature, if we want to get an equation that involves volume by saying that from the equation that PV is equal to nRT, we know that T is equal to PV divided by N times R. So let's go from this line. Let's replace T with PV over NR. So we'll have PV over NR multiplied by V to the gamma minus 1. That's going to be equal to a constant. But N and R are going to be constants. We're going to assume that N is constant in this process. Or will be constant for the processes that we're going to talk about. So we're going to absorb N and R into the constant on the right-hand side. But then we can also say V times V to the gamma minus 1. What's that equal to? If you have something like x to the 3 multiplied by, well, we'll use an n. If you have something like x to the n, right, and you multiply that times, nope, that's not what we're doing, is it? We're taking x and we're multiplying times x to the n minus 1. That's what we're doing. What's that equal to? You add the exponents, right?
X.
So this is just x, it's not x, it's x to the n. You add 1 plus n minus 1. So we'll do the same thing over here. V to the 1 plus gamma minus 1 will just be gamma. Then we absorb everything into the right-hand side. So we get PV to the gamma is a constant. And we can turn that into an equation 2. Pressure 1, volume 1 to the gamma is equal to pressure 2, volume 2 to the gamma. Another pretty handy relationship. Now, something to keep in mind, just to remind you what we're doing here. These are only going to work for... What type of process are we talking about here?
Adiabatic.
Adiabatic, that's right. This is only going to work for adiabatic processes, okay? But it works for those. All right. Now, the next thing we can do is we can find the work done in this process by saying that we know Q is equal to 0 and we know delta U, we set it from above, was equal to NCV times the change in temperature. So we can then say that the work is equal to the negative of this, negative delta U, so negative N times CV times, let's say our change in temperature, we call it T2 minus T1, for example. Okay. Then what we can do is We can absorb a negative sign into our equation here. So now the work is going to be equal to NCV multiplied by T1 minus T2. And then the last step we want to do here is to use the ideal gas law equation again. So we want to replace the temperature with this, PV over NR. So then the work done is going to become NCV. This will be P1V1 over NR minus P2V2 over NR, right? And almost did this perfectly. I almost had exactly enough room. And then we pull out the n's, so the n's cancel. We pull out the r's, so we have CV over R multiplied by P1V1 minus P2V2. And then CV over R, I think, was gamma minus 1, right? Oh, it's 1 over gamma minus 1. Here we go. R over CV is gamma minus 1, so CV over R is 1 over gamma minus 1. So this is going to be work is equal to P1V1 minus P2V2 over gamma minus 1. So we got that equation, we got this equation, and then we got the other two equations, which were P1V1 to the gamma equal to P2V2 to the gamma, and T1V1 gamma minus 1 equals T2V2 gamma minus 1. So these are all of our equations. They're all kind of related to each other. I mean, the way you go from this equation to this equation is you use the ideal gas law. That's all we did, right? And the way you go from this equation to this equation is use the ideal gas law. So there's really just two equations here. One for work and then one that relates to pressures and volumes and things like that. Again, all of these are only going to work for an adiabatic process. But we've got one that we can talk about here. Adiabatic compression in a diesel engine. Finally, here we are about, what are we, 2 months in? 3 months in? We're like 3 months in, right? We're 3 months in and we're finally talking about engines, which I think is pretty much the most important part of Physics 1B, is to learn how we can take these ideas of thermodynamics and use them to do work for us. And the primary way in which we're going to see that is in the form of an engine. The next chapter is all about something called heat engines, and a diesel engine is just one example of a heat engine. All right, so let's read this problem. It says the compression ratio of a diesel engine is 15 to 1. That is, air in the cylinder is compressed to 1/15 of its initial volume. So the initial volume is this, and the volume here is this. This is like the compression that occurs in one of the strokes in the engine. Imagine this is like one cylinder inside of a car. You know, if you have, for example, a V8 engine, it means it has 8 cylinders, just like this, that are pumping in and out in the process. We're just looking at one portion of this process, though, where the piston drives the gas down like this, causes it to compress. The next step would be that the gas would be compressed, which would lead to an explosion. That explosion would then drive the expansion back out. And that process to go from compression to expansion to compression to expansion is ultimately the type of cyclic process that occurs in your car. And with each stroke, you get energy out of the process. The gas here ends up doing work on your car to make the wheels move, right? So, that's how you can take the stuff we're talking about and turn it into something that is applicable, i.e. like a working engine, right? But we're just looking at one part of that. It says the compression ratio is 15 to 1. That is, air in the cylinder is compressed to 1/15 of its initial volume. So here's V1. It says V2 is 1/15 of V1. If the initial pressure is 1 times 10 to the 5 pascals, so let's call that P1. So this is 1 times 10 to the 5 Pascal. And the initial temperature is 300 Kelvin, so we'll call T1 is equal to 300 Kelvin. Find the final pressure and temperature after adiabatic compression. Okay, so we need to find what is the final temperature. We'll call that one P2. We'll find what is the final temperature. We'll call that one T2. And we know that V1 is just equal to V1, and V2 is 1/15 of whatever that is. Right? So part A, find these two. That's part A. Okay. Part B, how much work does the gas do during the compression if the initial volume of the cylinder is 1 liter? And it tells us to use the values of CV equal to this and gamma equal to 1.4 for air. It's kind of redundant because if you know one of these, you can find the other one, right? All right, so let's put those down here too. We have CV is 20.8 and gamma is 1.4. Now these problems often have multiple ways that you can do them, so what I want to do, because we have so much time left and this is the last thing we're going to do, and I could just rush through it and we can end early. I don't think that you would learn as much from that though. So let me write down here the equations that we just got. So the equations were P1 V1 to the gamma should be equal to P2 V2 to the gamma, and TV to the gamma minus 1, 1, 1, is equal to TV to the gamma minus 1, 2, 2. And the last equation we're going to need, because we're going to need to find work as well, was that work was equal to P1 V1 minus P2 V2 divided by gamma minus 1. And I think if we do it this way, we won't actually need the other equation. I think that's all we need. So I want you to try to solve part A, and I want you to try to solve part B. And like I said, there's more than one way to do it, so feel free to choose your own method, okay? I'll give you 5 minutes, and then we'll solve it. There's a way to get this to just do a timer for me. How do I normally do that? Yeah, whatever. Okay. Take 5 minutes, try to solve. Maybe just focus on just part A for now. And if you finish that one, you can also do part B. Okay, that was 5 minutes. Whether or not that was enough time or not to completely solve the problem, not a big deal. Just give you some time to think through it while I'm not talking is the idea. Alright, so I'll ask in a second if you got an answer, but we're going to talk about some things first. First of all, why can't we just do this? This is one of the first things we learned when we talked about the ideal gas law, right? Why can't we just do this? Yeah, there's 2 unknowns, right? And it's only one equation, so we can't solve it exactly. All right, well, that's fine. So let's, now that we understand why we even, that's another way of asking, why did we bother to derive all this junk over here on the left? And that's basically the answer. All right, so, all right. We want to find, let's do P2 first. So we'll use that equation. So this tells us that P2 should be equal to V1 over V2. They're both raised to the gamma power, so we'll just do this. Times P1. So that's going to be V1 is, well, it's V1. V2 is V1 over 15. This is raised to the 1.4 power. And we multiply that times pressure 1, which was 1 atmosphere, or 1.01 times 10 to the 5 pascals. So basically, this times 15 to the 1.4. What do you get if you calculate that? You want to get this answer before already? Did any of you get this during that time? What'd you get? 4.5 times 10 to the 6th pascals, so about 45 times 10 to the 5 pascals. Let's write it like that just because I think it's easier to see what's going on. So 45, there's a 4.5 and a 4.4, so we got some issues here. I guess I'll do it myself. 15 to the 1.4 times 1.01 E5. I got 45, or 4.48, let's say. We'll write this as 44.8. That's going to be, times 10 to the 5 pascals. So a huge increase in pressure from about 1 atmosphere to almost 45 atmospheres of pressure. A lot of pressure in there. That's fine, Ryan. No big deal. Okay, so next we want to find the temperature T2. Probably the easiest way to do this now is this. Just use the ideal gas law. Oh wait, we don't know how many moles there are. We can't do that, right? Yeah, we don't know how many moles there are. So we could figure out the number of moles if we wanted to, but that would require a whole nother calculation, so we might as well just avoid doing that. And instead what we can do is we can use this equation. This tells us that T2 should be equal to V1 over V2 to the gamma minus 1, which is going to be 0.4. You know what? I shouldn't do that. We'll just write it. We'll do 2 steps. Gamma minus 1, and then we multiply by T1. That's going to be V1 over V2. We already saw the ratio there is 15. And we raise that to the gamma minus 1, which is 0.4. And we multiply by our original temperature, which is 300 K. And we get, what did you all get? 754. Let's see if I agree. 15 to the 0.4 power times 300. I got 886. Did I do something wrong? Okay, it's 886. All right, cool. Yeah, 886 Kelvin. I find these to be it's kind of weird. You don't do much in physics or really anywhere in science, right? Where you have these really strange powers. 1.4 and 0.4, right? We never do anything in science like that, right? It's always like squared or cubed or I mean, sometimes, I guess, I'm thinking about my physics 1C class. Sometimes it can be some random number like this, but it just, I find it to be kind of interesting that it's exactly 1.4, or really, if you think about it, it's 7 over 5, right? I don't know why. I find stuff like that to be kind of fascinating. Okay, so that's T2. That was T2, and this was P2, right? All right, there we go. Pretty straightforward. The final part is to find how much work does the gas do during the compression if the initial volume of the cylinder is 1 liter. So we can use that equation now. Make sure I wrote it down right. P1V1 minus P2V2 over gamma minus rho. It looks like we wrote it down right. Okay, so then we have, let's do a different color for this. So this is part B, this was part A. So work equal to P1V1 minus P2V2 over gamma minus 1. This will be, P1 was 1.01 times 10 to the 5th pascals times V1. We're saying it's going to be now 1 liter, or 0.001 meters cubed, minus P2. P2 was 44.8 times 10 to the 5 pascals. We have to multiply by V2, which is 1 over 15 V1. So that's going to be 0.001 meters cubed divided by 15. Now we can see pretty clearly that this number is going to be negative, right? And gamma minus 1 is 0.4. I guess I don't have to write it like that. I can write 1.4 minus 1. Because if we think about what happened in the process, the volume only decreased by a factor of 15, but the pressure increased by a factor of like 45, right? So we know this is going to be a negative quantity. Is it reasonable that it's negative? I don't know. You tell me. You get negative 490, basically? Okay, I trust you. I'm just going to plug it in and see what I get with these numbers. So I'm going to use exactly the number that I got from before. I mean, I'm not going to round it off, so we're going to use whatever numbers in my calculator here. For the pressure, 2 divided by 15, and then we divide the whole thing by 0.4, which will make it bigger. Giggity, that's not right. Times 0.001 equals divided by 0.4 equals 493. That's what I got as well. Okay, so you get negative 493 joules. And just like the first question at the beginning of class tonight, we ask, why is it negative? Don't we want engines to do work for us? Why would we have negative work here?
Efficiency.
No, that's not the answer. Why is it negative?
Either the engine's being done, work is being done by the engine.
It's the compression stroke, so it's negative, right? The volume of the gas decreased, right? We say in the past that the only way that a gas can do work on its environment is if the volume changes, right? And in this case, the volume got smaller. So since the volume got smaller, that means that the environment is doing work on the gas, right? The energy is going to come from the next step of the process where now the gas is going to explode, right? You compress it down, which causes an explosion. That explosion will then naturally drive this back out. And as long as you have the work done by the gas in the next stroke be greater than 493, even if the next stroke only gave you 494 joules of energy, you're still getting 1 joule of energy. And if you repeat that process a whole bunch of times every second, right, then you'll get 1 joule of energy every time you do it, right? This is why inside of your car, you'll notice that you have like your tachometer, which tells you the number of RPMs of your engine, right? And let's say your engine is running at 300 revolutions per minute, right? what that means is that it does that stroke, right, of, compression, expansion, compression, expansion, compression. It does it 3,000 times every minute, right? And you could divide by 60 and say that it does that stroke, 50 times per second, right? So if you're getting 1 joule 50 times per second, then that leads to 50 watts, right? Did that make sense? If you get 1 joule on every stroke, that leads to an output power of 50 watts. That's not much, right? So you want to get more than 1 joule out of the system, but that's what the whole next chapter is going to be about, is about learning that process and how do you make these systems more efficient, which is what Andrew was mentioning, and then make it so that we get the most energy we possibly can out of these internal combustion engines. So we'll be talking about that in the next chapter, so be sure to read chapter 20 before next time. I think the next time I meet with you will be on Monday night for the next lab we're doing, which is F-3. Might be worthwhile to mention something about this lab. So F-3 is going to be another statistics lab. And you could probably read all of this before you come to class. Shouldn't be, the theory is not particularly challenging. It's about least squares. We're also going to be talking about random walks. And then you're going to be doing an actual random walk. The random walk, we should talk about the random walk. Because this is something that's really fascinating. We have a little bit of extra time. So the next lab we're going to be doing is going to be discussing this topic. So the random walk is something that shows up in physics where the idea is you start off at one location, you can only move left or right, and you use something to randomize whether you move left or right, okay? We call this a random walk. This is a really important thing in thermo. It's a really important thing in other things that I'm going to compare it to here in a second. So the random walk, this is where you start at one location, let's say on a number line, for example, okay? And you flip a coin. Okay? If you do heads, you go 1 right. And if you get tails, you go 1 left, okay? Right? So you flip a coin, let's say you get heads, you move to here, right? So now you're standing here, right? Flip a coin again, let's say you get heads again, you can move to here. So you get heads again, you move to here. Okay, and then let's say you keep flipping it and then you get, I don't know, maybe you get a tails, you move back 1. Then you get a couple heads again, you move over a couple more. Then you get a few tails again, you're back maybe over to here. The point is that after some amount of time, you're going to be at some new location, right? And this is what we call the random walk. We use it in statistics and in physics as a way to model randomness in the system. And it's even used in the stock market as a way to predict and understand the fluctuation of prices of stocks. Anyway, Ryan Taylor asks, if car fuel gas is a liquid, yet in this engine we are compressing a gas, so does this car have a chip to change the liquid into a gas, or really what is going on? I believe what happens is you have a gasoline-air mixture. It's a mixture of gasoline and air that is in the system here. Does that sound correct to those of you that know a lot more about cars than I do?
I want to believe that since it's like high pressure, doesn't the temperature go up and then the gas evaporates, hopefully?
Yeah, probably something like that. Seems reasonable to me. So you're saying if it comes in as a liquid plus... Right. Exactly, Louis. Where'd you get that? That's exactly... Yeah, random walk theory suggests that changes in stock prices have the same distribution and are independent of each other. Therefore, and by the way, to answer your question further, Ryan, I would highly suggest that you just go read about how an internal combustion engine works. Off the top of my head, I don't know the answer to your question, but I do think Andrew's on the right track. That during the combustion process, it probably vaporizes the gas. I think that's correct. And then it's a gas-air mixture is what's inside of the system itself. So the last part of this is the most important thing, and I talk about this quite frequently in my class. I don't know if you find this offensive or not, but oh, there you go. They use fuel injectors, which atomizes liquid fuel. Thank you, Jacob. There you go. Basically, yeah, turns it into a vapor, right? So here's the thing about what Louis said that I think is really important. It assumes the past movement or trend of a stock price or market cannot be used to predict its future movement. What does that mean? That means that at some point in your life, okay, you're all going to have jobs, right? And you're going to start thinking about saving money, right? When that occurs for you, that doesn't matter, you know what I mean? But I'll tell you this much. You should start saving money as soon as you possibly can. As soon as you're making enough money to pay for your getting back and forth to your job, you can pay for your rent, you can pay for all your food and all that stuff, and you have a little bit of extra money sitting around, you're probably going to want to do things like you're going to want to travel, you're going to want to do things like you're going to want to buy new cars. That's fine. Do whatever you want. Live your own version of the American dream. You're all free to do whatever you want. But at some point in time, you're going to have to start saving money for retirement, okay? And at some point in time, you may decide that you just want to make money off of your money. And keeping your money in a bank account, whether you know it or not, is a terrible, terrible, terrible idea. Because if you leave your money in a bank account, you don't get any return on the money, or you get a very small return. The return on a savings account is usually something like 0.005%, which is pretty much nothing. If you invest your money in the market, the stock market, which you may or may not be afraid of, or you may have been told is like gambling or whatever, you'll get something like between a 20 to 30% return over the last few years. At the bare minimum, you'll get something like a 10% return on your investment from the market. But you may be thinking, oh, but if you invest in stocks, like don't the stocks sometimes go down? And the truth is they do. But the reality is that if you hold your stocks over a long period of time, you will make money. You'll be guaranteed to make money. And this is because the US economy grows at a certain rate every year, the world economy grows at a certain rate every year, and the stock market almost always beats that. Okay? There are going to be times when the stock market doesn't do as well, but it's very rare. So why am I telling you about this? I'm telling you about this because throughout your life, you're going to run into people that are going to try to lie to you. And they're going to try to tell you that you should spend your money on this, or you should spend your money on that, or that you should sell a stock, or you should sell an asset. Like a really good example of this is something like Bitcoin, for example. They're going to tell you, oh, you should sell that. That thing's not worth anything, and it's going to tank in value, right? What I've found in my life, and what I've seen through doing whatever I can for studying all this stuff, is that because of what Louis said, because you cannot predict the future movement of a stock based on its past movement. Now, keep in mind, people think they can, right? People think they can. You will find websites where you can go read about people that will actually look at stocks. They'll look at the pattern that the stock has gone on, and they'll try to use it to predict what's going to happen in the future. These people are lying to you. Whether they're talking about stocks, cryptocurrencies, or whatever they're talking about, they have no way to predict the future. Because in reality, it's just randomness, right? So at some point in your life, you need to start saving money. Technical analysis, you even know what it's called, Brian, so you know what I'm talking about. Technical analysis is bullshit. It's not science. And anyone that really, truly understands how these things work know that it's a waste of time. Okay, technical analysis is where you look at a stock chart, you draw all these special lines on it, and yeah. I remember I had a finance student one time that took this class. It wasn't 1B, it was like 3B or something like that. It was a different version of this, or 2B. But we were talking about thermodynamics, and this topic came up. And he was convinced he believed in this technical analysis stuff and thought that he'd used it to make a lot of money. When in reality, he hadn't really made a lot of money. He had just it doesn't really matter. The point is that I actually convinced him that what I'm saying right now is true. And this is someone that really came into my class believing that technical analysis was a real thing. And just with like a 30-minute talk like I gave you now, he believed by the end of class that it wasn't true. So, all right, so this is the kind of like final statement of this. You need to start saving money at some point in your life. The biggest factor in terms of the amount of money that you will make that you'll be able to use at retirement is, does anyone know what it is? Is it the amount of money you invest? Is it the time that it's invested? What do you think is the most important thing? The time that you have invested, or the money you start with? Compound interest, so time. That's right, total time. That means the sooner you start, the more money that you're going to make, basically. Einstein said that compound interest is the most powerful force in the universe. This is coming from someone who really understood the forces of the universe really well. You can make so much money off just putting your money into a stock and never, ever, ever selling it. It's crazy. It's crazy. Like, it blows my mind that this works. Because you hear people talk about being like savvy investors and stuff like that, and they talk about, oh, you gotta buy at the right time and then sell at the right time. It's all bullshit. You just need to get your money in the damn stock market and let it sit there for years, and you will be shocked at how much money you make. Even if you only manage to, let's say you could only save like $1,000 in the first year that you're saving, and you put that into the stock market, and then the next year maybe you find the ability to save a little bit more, right? As long as you just put it into a stock and never sell it, you will make so much money. And you can even put it into just simple things that are called index funds. Index funds basically just track like the Dow, or they track like the NASDAQ or something like that. You like the app Acorn because it shows you graphs of how much money will be worth. There you go. That's great. That's wonderful, isn't it? See, Ryan's on top of this already. So anyway, physics is important. You guys are all going to be engineers. You're all going to be computer scientists, or you're all going to have good jobs, is what I'm trying to say. And you're all going to be making a decent amount of money. I just cannot emphasize enough that you need to start saving for retirement early. It does not... Oh no, here's the great thing, Jacob. You don't even have to sell them, because you just sell portions of your account. You don't have to sell everything. You sell portions of it, and that way it can continue to grow. But that's basically what you would do, yeah. You would sell off some portion of your portfolio, and then hopefully it's big enough, yeah. Robinhood's easy to use, that's right. It's true. Just get some money in there. Even if you could only put $500 away this year, it would be more valuable than, like, let's say 5 years from now, you'll have a real job. Maybe you could put away $5,000. The money you put in now is going to be more valuable than the money you put in later. That's all I'm saying. Coinbase, that's a great, I don't know how you feel about cryptocurrencies. I'm not going to encourage you to invest in them or anything like that, because they are very volatile, but it is a store of value. I've made a lot of money off of just putting money into Bitcoin like 5 or 6 years ago and just never touching it. It just makes money. Anyway, I know this doesn't have anything to do with physics, but it kind of does, because we're talking about the random walk on Monday, and random walk is connected to stock markets. And I wish someone would have told me this stuff when I was 21 years old, because I didn't start saving money until 2009, which is, how old was I then? I was 28 years old. So, yeah. What I think about NFTs, you find it pretty unbelievable. Anything is a store of value. They're kind of new, so they're kind of risky, right? I wouldn't put a lot of money into them or anything like that, but you could make a lot of money off of them technically, right? I'm not going to tell you what to invest in. I'm not going to tell you if I think something's good or bad. I will say that I think the stock market is pretty safe. And I think Bitcoin's pretty safe, but I think that's a pretty controversial opinion. What's EV? What is EV? Just expected value? Electric vehicles? Oh, okay. So you're investing a lot of money in electric vehicles. That's a good place to invest. It's definitely something that's changing. Yeah, lithium. Yeah. Okay, I'm going to stop right there. Anyone have any questions or anything about the class tonight, about adiabatic stuff or anything like that? Here's the other thing. One more thing. One last thing. If you do anything tonight after you get off, you should probably work on your homework and all that kind of stuff. You should go read about this, if you haven't heard of this before. A Roth IRA. So a Roth IRA is an investment device where, and I'm not trying to get you to buy something. This sounds like I'm trying to get you to buy something. I swear to God, I'm not. I'm trying to help you to do something for your future. This is something that has a maximum amount you can invest per year. So it's something where the government says you can put your money in an account like this. Okay? Yeah, Fidelity offers Roth IRA. That's what I use. I use Fidelity. So a Roth IRA is an account that allows you to put no more. So there's a maximum, basically. The max you can invest is $6,000 per year. And it changes as you get older. Maybe it's less for you. $6,000 per year, okay? $6,000 per year. So some of you already have this stuff. You all are very smart. You all are very smart. So not $60, but $6,000 per year. Just think about this. There's this thing, and the government tells you there is a maximum amount you can put in. And the reason why they do that is because if they didn't put a maximum on it, people would make too much money off of this. So the cool thing about this is that you always pay taxes on your income, right? A Roth IRA is such that when you withdraw it, you do not have to pay taxes. Which means that you pay taxes when you put the money in, because you always pay taxes on the income that you earn, right? But when you cash it out, you don't pay any taxes. Now, if you actually do this and you put like $6,000 a year in, you can do a pretty simple calculation if you understand how to do compound interest stuff. It's not hard. You can just go read about compound interest. You'll find out how to do it. If you start saving when you're like 20 years old and put $6,000 a year in, you'll have something like $10 million when all is said and done, right? And it's $10 million of like tax-free money. Can you imagine that? That you just have income that's tax-free and you're like 65 years old and you don't have any, you've already probably bought a house and stuff like that. Anyway, if you've never heard of an IRA before, you should get one now. You should start saving now. The faster you do it, the better. If you have any ability to put any money away a month, you should put it into this. All right, that's my life advice for you all tonight. I found that I didn't get any of this advice when I was a kid, but when I opened a Roth IRA, I remember at the time I was living in Stillwater, and when I went to grad school, and I sat down on my computer, and at the time I was using Mathematica all the time because Mathematica was my the thing I used to do a lot of my theoretical high energy physics calculations, right? And I was like, wait a minute, let's do a calculation. I did this calculation, and I couldn't believe, even if you put a very marginal rate of return, even if you only have like a 5% rate of return, you will make so much money if you just only did this. If you only did this. And imagine what you can do if you invest in even more things, you know what I mean? They think they tax 40% of your profits when you sell. No, it's not that bad. Capital gains tax is like, I think it's only 15%, Andrew. It's not that bad. But it's something. 15% on like $1 million is a lot of money, right? It's $150,000. Used to work for a bank. The only good thing you got from it was that Roth IRA. There you go. There you go. I used to work at a bank too. That's not where I learned about this stuff. I learned about this stuff just from talking to my parents and reading things and all that kind of stuff. Yeah. Okay. Anyway, I'm gonna stop the stream right here.